Hi, in this video we want to show you, by means of the simulation of the Langevin equations, the appearance of the ergodic hypothesis. So, the ergodic hypothesis, we have already seen that, is the way by which we look at our quantum mechanical system. We may look at it as an ensemble, in which case we perform our averages, letting the system go for some time and fixing a time t equal to 0, and then making the averages by looking at each system of the ensemble and making the averages in the usual way. Another way of looking at the averages is by assuming that we have just one system, a single system, and assuming a time window by which we will make continuous experiments to get some the property of the system, and then we make the averages by adding all these results for a single system. So we have assumed in the videos that we have just done that the ergodic hypothesis applies to quantum mechanical systems. This is not obvious, then we will show using the simulations how this happens, in this case for the harmonic oscillator quantum mechanical system. Let us see. We again have our simulator. We are assuming the harmonic oscillator system for a single system here. We use 400,000 points in the trajectory, and we will try to see the result of that by showing the probability density function. Of course, this is what we have obtained for the probability density function in a previous simulation. I will do the simulation again for n equal to 2, the second excited state of the harmonic oscillator. So let's just make that again. We will increase the number of points in the trajectory. Look at this. Look how the probability density function upon configuration space changes with the course of time, but goes to a situation which is asymptotically equal to the one that we get from our quantum mechanical calculations. So this means that this change in the probability density function means that our function is passing from one part of the system to the other. We can even say in which region of space that particle is, because we are seeing that the probability density function is increasing or decreasing with the course of time. So in this case we are using just more 400,000 points in the trajectory. We are adding with the previous simulation that we have done in the previous video. So our probability density function probably will give a better result, a better fit with the calculated theoretical one. You see, now we know that the particle is in this side of the configuration space, because this is we see that the probability density function is increasing here. This is very interesting to see. Now we know that it is on this side, but look that now the difference has become smaller because we have a lot of points in the trajectory. So we are moving toward stable situation. which is of course what the Schrödinger equation gives us. The Schrödinger equation gives us, as we have seen in the demonstration of the Langevin equation, the Schrödinger equation gives us a stable situation, not a transient one. The simulation is just finishing. I'm presenting a lot of things here, so this is why it's taking more time. I will remove these other elements in the next simulation. You see that the fit is almost perfect. So let's change these. Don't want to see these. It makes not much sense for uh, ensemble approach. But now I will show you the behavior of the system for ensemble simulation. I will change here for the ensemble simulation. I will wait for 2000 small intervals of time before I make the averages, or of course the the calculate the density function in each little box here in the configuration space for 1200 systems. Okay, let's do the simulation. The simulation is quicker. Let's see what happens here. And this is what we get. See, we get exactly the same result. So the two results, one for the single system and the other for an ensemble of systems, are just equal, and this is what we mean by the ergodic assumption. We may do that for another, for instance, a quantum mechanical state. Now we have the first excited state. Let's make the simulation for the ensemble simulation. So let us see. Okay, we are now almost getting the result. Look that again we get the same result for the probability density function. We will now change for the same quantum mechanical state for the single system approach and see what happens with the result of the stochastic simulation. Let us see. You see here that this is a single system with 400,000 points in the trajectory. So let us see. Look at the transient situation, how this situation will having large changes here. The particle is passing from one region of the configuration space for to the other. I may make the simulation again with more points if you want to see that this improves the result. I will put 1 million points in the trajectory and make again the simulation to see that the results improve. Of course, it's expected that the results will improve because we are including more points in the trajectory, so we are spanning a larger time interval in the uh, time line. Look that the probability density function is almost converged to its theoretical result. The amount of change here when the particle passes from one region to the other is very small. Look what we get here is a very much better result as expected. And again, this shows that we have here the ergodic principle in action. So again, as we have already said, you have just seen with the simulation. The two approaches, the ensemble and the single system approach, and you have seen that they give exactly the same averages, because if they give the same probability density function, of course, they will give the same averages. Okay, in the next video, I will show you, by means of simulations again, of course, how one may have the Newtonian limit of quantum mechanics. Thanks for watching.